Hey everybody, this is Remy, and this video is going to cover the Chapter 3, Section 5 note outline for Math 126, and it's entitled Complex Numbers. So this section actually might be a review for some of you. So I'm going to start off by talking about the number I. So the number I is defined such that I equals root -1, and then if you square both sides of this equation, you would get that I squared equals -1. So I is a specific number. It's not a variable, kind of like the number pi or e. So I is useful when you have the square root of negative numbers, which before we weren't considering. And now if we come across square roots of negative numbers, we can write them actually involving the number I. So this example, we're going to express each number in terms of I. So since this one has the square root of a negative number, we can take the square root of that -1 inside, because it's -1 times 21, and we can just pull I out and write root 21. And you could also write it like this, root 21I, but because of the root, we actually usually put the I in front of a root so that it doesn't get mistaken. You don't accidentally draw the line on top of the I. So either way is fine, but this creates less confusion. And then part B, we have a negative out in front, negative, and then since it's a root of a negative number, we can pull out an I, and then we'd be left with root 15, and that can't be broken down, just like the 21 can't be broken down. So we get negative I root 15 there. And then this one is similar to B, so we have negative out in front, and then pulling out an I from the root of the negative number, and then we're left with root 36. But this time, of course, root 36 we know is 6. So we have negative I times 6, and when we have a number like that that's not in a root, we usually put the I at the end. Negative 6I. And then lastly, this one is more like the first one. So we'll just have root -48. So the negative part inside lets us take an I out, I root 48. And then 48 can be broken down because it's 16 times 3. And then, so we can take square root of 16, which is 4. And then the I, and then root 3 left inside. Okay. And so this brings us to complex numbers. So this is a number in the form a plus bi, where a and b are real numbers. And then a and or b, these numbers here, they're real numbers, and they could also be the number 0. So that might happen. And the number a is said to be the real part of a plus bi, and then the number b is said to be the imaginary part of a plus bi. And sometimes bi is considered to be the imaginary part. It just depends on the book, but usually it's just the number b. And then if you're trying to incorporate I in your work, that number works similarly to how a variable would work, but just keep in mind that I is not a variable. It's a specific number. It has a true value. It's the square root of -1. Okay, so here we're going to add or subtract and then multiply. numbers that involve complex numbers, but it's really similar to what you've done before with variables, just combining like terms. So for this expression, of course, we have this minus here, so we know what to do with minus across the parentheses. We have to distribute the minus. So we get -9 plus 2i, and then minus a 3, and then plus a 4i. Because we have minus and negative becomes the plus, and then from there just combining like terms. -9 minus 3 is -12, 2i plus 4i is plus 6i. And so the number -12 is the a, the real part, and b is 6, the imaginary part. Okay, and then this one here, we can technically distribute the plus, but we know that that doesn't change any of the signs. So we have 2i plus 3 minus 4i, and then we'll just do the real part first, which is just 3 in this case, and then the imaginary part, 2i minus 4i, is minus 2i. So here the imaginary part, or the real part, is a, 3, and the imaginary part b is -2. Okay. Now getting into multiplying. So for this part, I'm going to handle this root first. So what would this be? It's the square root of a negative number, so we know we have an I, and then root 64 is 8. So we have 8i times, same thing over here, it's the square root of a negative number, so we have an I, and then it's square root of 16, so 4i. And then 8 times 4 is 32. I times I is I squared. But what does I squared equal? We can simplify I squared even more because we know the point of I, it's defined such that I squared is -1. So down here we'll replace I squared with -1. So 32 times -1 is -32. And now it's fully simplified. Then for part B, naturally we're going to FOIL. 1 times 2 is 2. 1 times -2i is -2i. 3i times 2 is plus 6i. 3i times -2i is -6i squared. Next thing to do is combine like terms. So we got this 2, that's the only real part right now. Minus 2i plus 6i is plus 4i. Minus 6 times what? 6 times I squared. I'm not going to write I squared again because we know it's -1. So -6 times -1. So we really have a plus 6 here. And then now we have another real part. We'll add that to the 2. So 8 plus 4i. And then if we're pointing out the real and imaginary parts here, in this case a is -32, and it doesn't really have an imaginary part, so what would be b? B would equal 0 in this case. We could write it as -32 plus 0i. And then this one, a is 8 and b is 4. Okay. And then let's do one more on the next page. There's no i's involved in this expression right now, but let's just rewrite it. Root 12 minus root -3 times 3 plus root -4. So we see that there's roots of negative numbers, so I is going to be incorporated at some point. So simplify. First I have a root 12. Well, that we know is root 4 times 3, so that's 2 root 3. So simplify that part. Minus root -3 is going to become I root 3. And then times over here, 3 plus, what's root -4? We've got an I, and root 4 is 2, so we have 2i. And now we can now that we've simplified the inside parts a little bit, now we'd move on to FOILing. So we have 2 root 3 times 3 is 6 root 3. And then 2 root 3 times 2i is 4 root 3i. And I'm just going to actually write it as 4i root 3, just because, like I was saying earlier, when we have this root involved, we usually put the I before it. And then next, minus I root 3 times 3, we'd get negative 3I root 3. And then lastly, negative I root 3 times 2I, we'd get a negative 2I squared times a root 3. Alright, so I'm going to combine these two because these are like terms. They both have I root 3. So 4I root 3 minus 3I root 3 is just 1I root 3. And then this I squared, what should we do with that? I squared becomes negative 1. So we get that. So in the next row we have 6 root 3 plus I root 3, and then this becomes plus 2 root 3. And now these two are like terms. 6 root 3 plus 2 root 3 is 8 root 3 plus I root 3, and now we can't combine these anymore because one part is real, one part's imaginary. A is A root 3, and B is just root 3. Okay, so now let's discuss powers of I. And we're going to start off by just considering each of these powers. So I itself is equal to what? The definition is that it's root negative 1. Okay, but I'm just going to call it I again. Then I squared equals what? I squared is negative 1. And then I cubed, we could say that that's I squared times I. Well, I squared is negative 1 times I. So this simplifies. I cubed simplifies to negative I. And then I to the 4th we could write as I squared squared. And then again, I squared is negative 1. So we have negative 1 squared, which is just 1. And then I to the 5th we could write as I to the 4th times 1. Or sorry, times I. I to the 4th times I would be I to the 5th. And what is I to the 4th? Well, we just wrote that. We said that I to the 4th is just the number 1. So we have 1 times I, which is just I. Let's keep going with I to the 6th. We could write that as I to the 5th, or actually I'm going to write it as I to the 4th times I squared. I to the 4th we said was the number 1. I squared we know is negative 1. So 1 times negative 1 is negative 1. I to the 7th, this one I am going to write as I to the 6th times I. And what's I to the 6th? Well, we just said that that was negative 1, so we have negative 1 times I, which is negative I. I to the 8th, this one I'll write as I to the 4th squared. And then let's go back, what was I to the 4th? I to the 4th was 1, so we have 1 squared, which is 1. And then we'll stop with I to the 9th, which is I to the 8th times I. And I to the 8th was 1, so we have 1 times I, and we're back at I. So there's actually a pattern happening. We have I, negative 1, negative I, 1. And then we have I, negative 1, negative I, 1 again. and then we're back at I. And then the pattern's just going to keep continuing on. If we keep finding I to the 10th, I to the 11th, and so on, it'll always go in this pattern. I, -1, -I1. I, -1, -I1. I, -1, -I1, and so on. So it's going in groups of 4. So since it's going in groups of 4, you could actually look at these exponents and think about if you divide it by 4, based off the remainder, if it's going to be one of these 4 results. So if you have I to some power, I to the n, divide n, the exponent, by 4, and then determine the remainder. So let's look, I guess, here. If you divide 5 by 4, what's the remainder? You'd be left with 1. And if you divide 6 by 4, you're left with 2. And 7 by 4, you're left with 3. And 8 divided by 4, you don't have a remainder. So if the remainder is 1, then I to the n reduces to I. If the remainder is 2, then it will reduce to -1. If the remainder is 3, it will reduce to -I. And if the remainder is 4, then I to the n will reduce to the number 1. So this is going to be the pattern, and doing it this way helps us when we have really large exponents. Okay. Like in the next example. So I to the 402nd power, there's a few ways to do this, but what I'm going to do is take 402. If you divide it by 4, we don't really care what the quotient is. In this case, of course, it's going to turn out to be 100, but we care about the remainder. What would be the remainder if you take 402 and divide it by 4? You'd have a remainder of 2. Therefore, I to the 402nd power, you look back, and if the remainder is 2, then we're supposed to get just the number -1. So I to the 402nd power is -1. Then part B, we have -I raised to the 39th power. And so I'm going to write -I as -1 times I raised to the 39th. And then when we have multiplication raised to an exponent, we know that we can have -1 raised to the 39th power times I to the 39th. And then what is -1 raised to the 39th power? 39 is odd, so we just get -1. And then for this part, we're going to do that divide by 4 trick again. So we're going to take 39 divided by 4. Don't care what the quotient is, but 4 fits into 39 9 times. But we care about the remainder. The remainder would be what? 9 times 4 is 36, so you have an extra 3. The remainder is 3. And if you look back, when the remainder is 3, it's going to reduce to -I. So -1 times -I is +I. So in general, the rule of thumb is any time that you run into an exponent of I that's larger than 1, when you're simplifying, then you must apply the divide by 4 rule to simplify as much as you can. Okay. Now let's talk about the conjugate of a complex number. So say you have a complex number, a plus bi, then its conjugate is a minus bi, and vice versa. And then a common notation is sometimes they will call the original number z, and then they call its conjugate z with a bar on top. So if you ever see that notation, z is the original number, and then z bar represents the conjugate. So for example, the conjugate of z equals 7 minus 6i is z bar would equal 7 all you do is switch the sign of the imaginary part. So instead of 7 minus 6i, it's 7 plus 6i. So those would be conjugates of each other. Or the conjugate of 15i, well, to find that, you just switch the sign of the imaginary part, so we'd get z bar is negative 15i. So those are conjugates of each other. And then we want to introduce this conjugate idea because we haven't done division yet in this section. We did addition, subtraction, and multiplication, but we need the conjugates to do division. So to divide a number by a complex number, then you multiply by 1, because you know that multiplying by 1 doesn't affect anything, but it's going to be in a particular form. It's going to be in the form of the conjugate of the denominator over itself. So we're looking for the conjugate of the denominator. So this example here, we want to divide 3 plus 2i by negative 4i. So that looks like this, of course. 3 plus 2i over negative 4i. So what the directions are telling us to do is we need to find the conjugate of the denominator. What is the conjugate of this denominator? It's negative 4i right now, so the conjugate would be plus 4i. So it says we want to multiply by 1 in the form of the conjugate of the denominator over itself. So we want to put 4i over 4i. And then we'll multiply. So really we're just multiplying by a fancy number 1 here. And then we already know how to multiply. So the bottom is easier. Negative 4 times 4 is negative 16. And then we have I times I, so I squared. And then on top, we just have to kind of distribute this 4i to each term. 3 times 4i is 12i. And then 2i times 4i is plus 8i squared. And then we know that anything I squared and higher, we need to simplify more. So this I squared, we know that that becomes negative 1. Times the 8, we'd get negative 8. Over, same thing with this I squared, we get negative 1. So negative 16 times negative 1 is 16. And then we just reduce as much as possible. So I have 12, I'm just going to split this fraction apart. 12 over 16i minus 8 over 16. 12 over 16i minus 8 over 16. This one reduces to 3/4 I minus 8/16 is a half, but it wants it in this a plus bi form. So we got to put the real part first, which is negative a half, and then plus the 3/4 I. Because a is negative a half and b is 3/4. Okay, so now we are on the last page of the notes, page 4, and doing another division example. We want to divide negative 7 by 2 plus 9i, which looks like that, and we're just going to do that same process. First, think about what's the conjugate of the denominator. So we have 2 plus 9i. The conjugate then would be 2 minus 9i. We have to put that over itself, so that we're really just multiplying by 1. And then we're multiplying fractions, so we just go straight across the top, straight across the bottom. The top, the negative 7 gets distributed, so we get negative 14, and then plus a 63i over, we could FOIL this out, but actually, this is like reverse difference of squares. We have like a plus b times a minus b. So that would be a squared minus b squared. So really we could write 2 squared minus 9i squared. It's difference of squares in reverse. So negative 14 plus 63i over 2 squared is 4 minus 9i squared. We get 9 squared times I squared. So we get 81i squared. And then let's simplify a little bit. Of course, We know what to do with this I squared now. Always replace it with a -1. So on top, we still have -14 plus 63i over, this will be 4 plus 81, so we get 85. And then again, we need to write it in this form where we have just the real part first plus the imaginary part. So we have -14 over 85 plus 63 over 85i. Okay, and then a big reason why we're talking about complex numbers here is because now we don't have to just consider real solutions to equations. And in particular, we're going to talk about quadratic equations and the complex solutions to those. So in the previous section, we talked about the fact that if we have an equation of the form ax squared plus bx plus c equals 0, and if b squared minus 4ac was less than 0, then we said that the equation had no real solution. So this was talking about, this came from when we would use the quadratic formula to solve this. We use the quadratic formula, there's a portion of the quadratic formula under the root that's b squared minus 4ac, and that was called the discriminant. And if that was less than 0, we just wrote there's no real solution. And now that we have complex numbers, we're going to say that in fact, if you do have b squared minus 4ac being less than 0, then there's actually going to be two imaginary solutions, or two complex solutions, however you want to say it. Complex, imaginary, same thing. This is spelled wrong. Okay. So now we are going to be able to use, to incorporate imaginary solutions as well as the real solutions. So this one, first we notice both of these examples are quadratic equations because we have x squared as the highest. So we have all our techniques that we've been using to solve quadratics. Very first one that you should always try though is directly. Can you just get that x by itself? Here we can. So the first thing we could do is subtract 9. We get x squared equals -9. Now to get rid of the x squared, or the squared I should say, we can take the square root of both sides. And we know that when we take the square root of two sides of an equation, we have to put plus and minus. So we have plus and minus root -9, and now we know that root -9 is just 3i. So we get two imaginary solutions, a positive 3i and a negative 3i. Also notice that these two solutions, plus 3i and minus 3i, are conjugates of each other. The two solutions are conjugates of each other. Okay. Let's do this one. So normally if I saw an equation like this, the very first thing I'm going to try to do is factor. Two numbers that multiply to 5 and they need to sum to 4. Well, you can't find two numbers that do that, so then you need to use more techniques. And the quadratic formula will always work. So let's just use that. A, and let's write down what A and B and C are. A is 1, B is 4, and C is 5. So using the quadratic formula, x should equal -b plus and minus the square root of b squared, which is 16, minus 4 times A times C, all over 2a. Then just simplify. Inside the root, we'll have 16 minus 20, which is which is -4, all over 2. And we used to just say that there's no real solution because of this negative. B squared minus 4ac inside here turned out to be less than 0. But now we have tools, we have complex numbers, so we can keep going. Root negative 4 is what? 2i all over 2. And then we can split this up. Negative 4 over 2 plus 2 over 2i. And so we reduce those, we get negative 2 plus 1i. So we have two solutions. Oh, I lost a minus. Plus and minus, plus and minus, plus and minus. Two solutions, negative 2 plus I and negative 2 minus I. Well, once again, the two solutions are conjugates of each other, and that will always happen. If you know that one particular complex number is a solution to the quadratic, then its conjugate will always be a solution as well. Conjugates, complex solutions always come in pairs of conjugates. Okay, so that concludes the 3.5 note outline.